Welcome students. Today we are going to study a topic in machine learning, that is dimensionality reduction. Basically, what is dimensionality reduction? See, the number of input variables or features which we provide to a data set is generally referred to as dimensionality. What is dimensionality? The number of attributes, the number of features which we provide to a data set. Those numbers of features or attributes are referred to as a dimensionality of a data set. Now, dimensionality reduction is another terminology which is mostly used for classification purpose. We can say that dimensionality reduction refers to techniques that reduces the number of input variables in a data set. In a particular data set, there can be number of features, number of attributes which may be present in a data set, but the dimensionality reduction motive is to basically reduce the variables, the number of input variables in a data set. Dimensionality reduction is simply the process of reducing the dimension of your feature set. Basically, dimensionality reduction is basically meant for reducing the dimensions from 3 to 2, 2 to 1 dimensions, and so on. Our feature set could be a data set with 100 columns, that is features, or it could be an array of points that make up a large sphere in 3-dimensional space. Here we are talking about reducing the dimensions of the feature set. So what is a feature set? Feature set can be anything. Feature set can be a data set with 100 number of columns, and these columns can be any type of attributes of a car, attributes or features of a car, etc. If we are taking a car data set, for example, then it may be a feature or attributes of different cars. Or it can be an array of points that make up a large sphere in 3-dimensional space. In a 3D space, we will refer to a circular object to be a sphere. So it can be an array of points in a 3D space if we are representing a large sphere. So this is what the feature set may be. Feature set may consist of these type of features. So the dimensionality reduction simply brings the number of columns down to say 20, or converting the sphere to a circle in a 2-dimensional space. So if the feature set which we discussed in the previous slide, that it contains so many numbers of columns or several dimensions of spheres, etc., like 3-dimension space, 4D space, 5D space, and if it is containing some graphical object, then what is dimensionality reduction is doing here? Dimensionality reduction will simply bring down the number of columns down to say from 100 to 20, or simply it will convert the sphere to a circle in a 2-dimensional space. So simply the feature set will be reduced from one dimension to another dimension, from a higher dimension to a lower dimension. This is what the principle of dimensionality reduction is. That is, a number of feature set is provided and it is containing number of features, but you have to basically reduce it to a lower dimension. This we can say that we are reducing the sphere to a 2-dimensional space. A 3-dimensional sphere diagram is reduced to a 2-dimensional space. It is represented by the vectors. We can say that if we are reducing the sphere from 3 to 2 dimension, or if we are reducing a feature set from 100 columns to 20 columns, then we can say that what is the need of doing such kind of dimensionality reduction. This is the one of the most important questions, that why we are basically looking into the concept of dimensionality reduction. What is the need to look up into this concept? So the main reason behind the dimensionality reduction performing is the curse of dimensionality. Basically, the curse of dimensionality is we can say a terminology that draws the attention for every data scientist to basically carry on this reduction technique. basically what is the curse of dimensionality? More input features often make a predictive modeling task more challenging to model, and more generally it is referred to as curse of dimensionality. See, if we are basically providing our training model a number of features, a number of attributes, then what will happen? The training model may get confused. The training model, after obtaining so many different features, so many attributes, the training model may get confused, and due to this the optimal results which are basically expected to be obtained from a machine learning model will not be obtained. So that is why dimensionality reduction is important, and the curse of dimensionality is too many features basically overfit the machine model. So this is the problem of overfitting or the curse of dimensionality. The problem of overfitting means too many features or too many attributes if are provided to a particular machine model, then the machine model will definitely get confused and it will not provide optimal results. So this is the basic problem of overfitting, which is called as the curse of dimensionality, and this is the that is why it is needed to basically carry on the reduction techniques or the reduction operations. So this is the basic concept behind dimensionality reduction, that why we are using dimensionality reduction, because of the problem of overfitting, which is basically called as the curse of dimensionality, that is too many features which are provided during the training of the machine model confuses the machine model. The curse of dimensionality refers to all the problems that arise when working with data in higher dimensions that did not exist in the lower dimensions. See, this is also a major big problem if we consider the curse of dimensionality. This is a major problem, that if we are working with higher dimensions, several problems are observed which is not observed in data sets which are lower in dimensions. So we can say that there are several problems which arise in higher dimensions which are absent in lower dimensions. So all those problems are basically, we can say the curse of dimensionality refers to all those problems. As the number of features increase, the number of sample also increase proportionally. The more features we have, the more number of samples we will need to have all combinations of feature values well represented in our sample. See, the concept which we discussed already, that is, as the number of features increase, the classifier performance gets degraded. The classifier performance gets degraded. Why? Because machine model is not basically getting to the best fit while providing certain number of too many features or too many attributes. So the basically the number of features, basically they are not optimal in results. The graph is showing that the classifier performance, we can say, is degrading as the number of features increase. As the number of features increase, the classifier performance is degrading. It is not providing optimal results. As the number of dimensions increase, the results which should be obtained in a clarified way are not obtained actually. So we can say this is the curse of dimensionality. As the number of features increase, the number of samples also increase proportionally, but here we can say that the performance of the classifier is degrading. Why to perform dimensionality reduction? As the number of features increases, the model becomes more complex. As we know that as the number of features or attributes increase, gradually the model becomes more and more complex. So the number of features, more number of features are there, more is the chance of overfitting. As we discussed earlier, that the problem of overfitting is the major problem which is involved, and that is why basically the reduction of the dimensionality is required. A machine learning model that is trained on a large number of features gets increasingly dependent on the data it was trained on, and in turn overfitted, resulting in the poor performance of the, on real data, beating the purpose. So we can say that a machine learning model, if it is trained on a large number of features, it is increasingly getting dependent on the data which on which it was trained on, and in turn got overfitted. Basically the main attributes somewhere are lost while getting overfitted, or if the machine model is getting overfitted, then the major attributes are overlooked during this. We can say that major attributes may be overlooked, and the classified model which is obtained at the end as an end result, it is not a perfect one. Problem of overfitting. Avoiding overfitting is a major motivation for performing dimensionality reduction. The fewer features our training data has, the lesser assumptions our model makes, and the simpler it will be. So we can say that if the training data has fewer features, our model will have to make lesser assumptions, and so as the model will be simple in design. Why is dimensionality reduction important in ML or machine learning? For example, a classification problem that relies on both humidity and rainfall can be collapsed into just one underlying feature, since both of the aforementioned are correlated to a high degree. Hence, we can reduce the number of features in such problems. See, humidity and rainfall, they can be correlated and collapsed into just one underlying feature, because they are both are related to a certain climatic conditions. So, a 3D classification problem can be hard to visualize, but if we are talking about a 2D one, whereas a 2D one can be mapped to a simple 2-dimensional space and a 1D problem to a simple line. So, we can basically reduce, if there is a possibility that we can reduce certain number of features into 1 from 2 to 1, then we should simply at once do it. Here rainfall and humidity are simply the features of a certain data set, that is the climate data set or weather data set. So, we can simply reduce from 2 to 1, that is the precipitation or the humidity may become a chance to bring a rainfall. So, rainfall may occur and humidity is also there in the atmosphere. So, these both are the attributes of a certain climatic condition or a weather. So, we can correlate it, it is certainly they are correlated with one another. So, we can reduce it to from 2 to 1 dimension. Need not to specify them in different dimensions, rather make it a common one. So, this will reduce our complexity. Dimensionality reduction simply reduces the complexity. The diagram which is explained below illustrates this concept, where a 3D feature space is split into 2D into two 1D feature spaces, and later if they are found to be correlated, number of features can be reduced even further. Here this is the dimensionality reduction which is being performed. This is a 3D object which is getting converted to basically the 1D feature spaces, and if they are correlated, then further division or the further dimensional reduction may be done over them. So, this is the dimensionality reduction example, where these 3D objects are reduced to a lesser dimension. Components of dimensionality reduction. There are two components of dimensionality reduction: feature selection and feature extraction. Feature selection, in this we try to find a subset of the original set of variables or features to get a smaller subset which can be used to model the problem. Then is feature extraction. This reduces the data in a high dimensional space to a lower dimension space, that is a space with lesser number of dimensions. In feature selection, basically they are trying to say that here we find a subset of the original set of variables or features to get a smaller subset which can be used to model the problem. Original set of variables or features is taken over here, and out of those important features are selected and reduced to a smaller subset. And feature extraction is what? It reduces the data in a high dimensional space to a lower dimensional space, that is a space with a certain lesser number of dimensions. So, this is feature extraction. There are various methods for dimensionality reduction, which includes principal component analysis, linear discriminant analysis, and generalized discriminant analysis. Dimensionality reduction may be both linear or non-linear, depending upon the method used. What is the method used? That is dependent on which type of dimensionality reduction will be performed on either linear or non-linear. The prime linear method called principal component analysis is discussed next. Now, principal component analysis. This method was introduced by Carl Pearson. It works on a condition that while the data in a higher dimensional space is mapped to data in lower dimensional space, the variance of the data in the lower dimensional space should be minimum. we can say that there is a condition which is provided in a principal component analysis, one of the methods of dimensionality reduction, that is when the data in a higher dimensional space is mapped to a lower dimensional space, variance of the data in the lower dimensional space should be maximum. See, the variance should be retained. Even though we are reducing the data set from higher dimension to lower dimension, the variance of the data set is basically should be maintained in a proper way, or must be a higher variance should be observed in a data set. This is the example scatter plot, and the dimensionality reduction points basically are illustrated in this next scatter plot. Here there are two basic principal components which are being shown in this type of scatter plot. That is, the first principal component divides the scatter plot into two equal halves. It is basically the first principal component is dividing the scatter plot into two equal halves with a straight line in a way that explains the most variance, that is, it follows the longest dimension of the data. And the second principal component cuts through the data perpendicular to the first. So the red lines are are basically the first principal component, and the blue lines are basically the, we can say this blue line which is getting falling perpendicular to this particular line is the second principal component. So the we can say the first principal component divides the scatter plot into two equal halves with a straight line in a way that explains the most variance, that is, it follows the longest dimension. This basically these points are we can say falling on this scatter plot. So if we observe this line from here, so a straight line will be observed to us from this particular direction. From different directions, the visibility of this particular data set points is different. If we observe it from here, the line will be different. If we observe it from this direction, the line visualization will be different, and from this direction if we observe the line data points, then the line visualization will be different. So basically it is used in visualization patterns or the data visualization or exploratory analysis. And the second principal component cuts through the data perpendicular to the first. Basically here the blue points basically are falling on this certain line. So this is the second principal component. So the first principal component is simply making a straight line, and the second principal components are falling perpendicular to this line. So these two, that is these red points and the points blue points which are falling as a perpendicular on these red lines are the second principal component. So there are two principal components which are present in this particular scatter plot. Now PCA, what does PCA do? It attempts to draw straight exploratory lines through the data like linear regression. So PCA will basically attempt to draw out the linear regression lines most. See, there will be several principal components which are involved in an analysis. Principal component analysis will involve several principal components to be found. Here we have found two principal components. If the view of this line is changed and taken observation from each and every direction, then several principal components may be obtained. It's not that necessarily only two principal components, but several principal components may be obtained. So we can say that PCA generally attempts to draw straight explanatory lines through the data like linear regression. It generally prefers to bring out the data in a linear regression manner. Each straight line here represents a principal component or a relationship between an independent and a dependent variable. While there are as many principal components are there as there are dimensions in the data, PCA's role is to prioritize them. See, so many principal components will be there if we do the analysis, but what is the PCA's role? It has to choose out the best one or to prioritize them, that which two or three principal components will be taken up, rather will be discarded. So here the principal component analysis plays a major role in the dimensionality reduction, and PCA is basically meant for providing the or prioritizing the certain principal components. Here these two principal components which are represented in this are the must one. These should be taken into account. PCA is a statistical procedure that uses an orthogonal transformation which converts a set of correlated variables to a set of uncorrelated variables. It is most widely used tool in exploratory data analysis and in machine learning for predictive models. Moreover, PC is an unsupervised statistical technique used to examine the interrelations among a set of variables. Several set of variables are present, and PCA finds correlations among those variables. It is a linear method. It can only be applied to data sets which are linearly separable. It is generally applicable, and we can say gives its best performance on linear data only. It does an excellent job for data sets which are linearly separable. But if we use it on non-linear data sets, we might get result which may not be the optimal dimensionality reduction. See, we can apply it on non-linear data also, but the results which will be obtained, it will not be a optimal dimensionality reduction. So generally PCA is applied on linear data sets, and it is generally applied on data sets which are linearly separable. Kernel PCA uses a kernel function. There is a kernel PCA term which uses a kernel function to project the data set into higher dimensional feature space where it is linearly separable. Generally there is a method of PCA also, that is called as kernel PCA, which tries to project its data set to higher dimensional feature space where it is linear, where it becomes linearly separable, which was earlier it was not possible. So it makes a non-linear data set to a linearly separable data set, kernel PCA. So we can say that kernel PCA is somewhat similar to the support vector machines. Now advantages of dimensionality reduction. What are the advantages of dimensionality reduction? It helps in data compression and hence reduced storage space. This is one of the most important we can say advantage of dimensionality reduction, that it helps in data compression, and so as the storage space required is less, and so it is reduced. Storage space required is reduced. It reduces computation time also. Computation time is also saved using the dimensionality reduction. It also helps remove redundant features if any. Similar types of repetitive features are generally removed in dimensionality reduction. Disadvantages are also there of dimensionality reduction, like it may lead to some amount of data loss. See, if we are reducing the dimensions, there is a possibility that some important features we may lose. Some important features may be we can say removed if we are reducing the dimensions. PCA tends to find linear correlations between variables, which is sometimes undesirable. See, PCA is such a technique of dimensionality reduction which is applicable only to linear separable data sets, and so this is the disadvantage. PCA fails in cases where mean and covariance are not enough to define data sets. Some statistical terms like mean and covariance, these mathematical statistical terms are basically, we can say, in these type of calculations PCA fails, and it is not enough, means it is not enough to define the data sets. In this case, in cases where mean and covariance are used, they are not practically enough to basically define the data sets, and we may not know how many principal components to keep in practice. Some thumb rules are to be applied. See, we have taken 3 to 4 principal components, but what is the proof that these principal components will definitely define the data set in a better way? It's not a proven fact that these 3 or 4 principal components which we have obtained from the dimensionality reduction, these are the best one. So here some thumb rules are to be applied. We cannot fully rely on the principal components which we have drawn out in the analysis. So we can say that some thumb rules are to be applied amongst those principal components which are chosen out of the dimensionality reduction. These are the references which I have taken for preparing this presentation. Thank you.